Okay. Somebody has some question regarding the resistance, especially these three parts. Okay. Actually, for these three parts, you need to consider, you look from the top to the bottom. This is only the contact window, and the bottom is another electrodes. So you have a first electrodes on the top and connect to the bottom electrodes. So for the cross section, you can consider to look back into the 3.3-1, this cross section here. So for example, you want to connect the aluminum wire to the bottom electrodes. The current bottom electrodes are highly diffused, highly doped area. So the area contact was through a small window here, right? The cross area you can see here is a opening area here for the contact from the top electrodes to the bottom electrodes. So if you have the contact from the top electrode to the bottom electrode, even though this is a square, you cannot count this the contact resistance as a square because you have a current come from a small area and expand to the large area. That means your resistance is reduced, right? Resistance is proportional to the cross-section area, inversely proportional to cross-section area. You have a large cross-section area, you have smaller resistance. Okay, so this is a combined case. It's not a simple case. So those things, the value you got here can be obtained by either theoretical calculation or by using experiment. Okay, it's not a simple question. Simple, things you can get it easily, but you can get the idea. Okay, so once you have this kind of contact from the top to the bottom through a small window and expand, so you can have a smaller resistance. Just keep in mind. Okay, so for example, this kind of connection, you have a 0.65 square. It's not a 1 square, it's smaller. And this one have an even smaller, 0.14. And this one's between 0.35 square. Okay, and the corner usually give you a similar results because you have a shorter current path here. Yeah, give you shorter resistance. Okay. So you got the smaller, the sheet resistance for this part, okay? Is all right? Just give some explanation. Okay, yeah. If no further question, we can go on for the next part, or we still have a lot of part. Wow. Okay, to go. So so let me quickly go through the diffusion system. You can take a reference later on for the process. Those are chemical reaction. So basically, boron diffusion, we can have three different kind of methods by using solid source, liquid source, or gaseous source. Okay, but the process is similar. Using different kind of source, you will bring the source to form like a gas to contact with the surface of your silicon at a high temperature. So in that case, the temperature will drive the your impurity get into your surface and contact with the silicon, and then diffuse into the silicon. Okay, so three different types, including the gas or solid gas or liquid. For phosphorus diffusion, they have a similar process, and also you have different sources. You can see different chemical reaction. So the furnace look like this. For example, the first one, you have a solid source. So the solid source will be put inside the furnace. The furnace looks like a tube, actually, large tube. And then you put your wafer on a boat. We call it a boat. Okay. So usually we'll put like 25 wafers, one box of wafers, 25 wafers, vertically on a boat, inside the tube of your process. Okay. So the tube included all those gas control things we call the furnace. So not only the solid source inside the cuvee, also we need to introduce some gas into the chamber for reaction. For example, like nitrogen and oxygen. So that's why usually after diffusion process, the surface will easily form silicon dioxide on the surface. That's why you need to consider the situation when you do the diffusion. If there's a silicon dioxide formed on the surface, different dopant will give you different. Let's see, where is it? Doping is here. Sorry, on the other lecture notes. Okay. Yeah, this part is also a difficult part. People usually don't understand very well. Yeah, this part, this 4 figure, right? So this 4 figure exactly just give the model. When we do the diffusion process, actually the surface is oxidized. So if you have a silicon dioxide on the surface, depends on the dopant. You have a different dopant. The silicon dioxide will have different behavior to your dopant. Okay, usually silicon dioxide like boron very well. Okay, but they do not like phosphorus or arsenic. They like p-type material. They don't like n-type material. Okay, so when you have silicon substrate, you have like a p-type material, like a boron inside the silicon, diffused inside the silicon. During the diffusion process, also you will do oxidation on the surface. So in this case, for the boron part, because silicon dioxide like boron, so the boron will be taken into the silicon dioxide layer. So in out, you will got a higher concentration of the boron on the silicon dioxide rather than the surface of the silicon. So you got some defect here actually, with a lower boron concentration, not as original you designed. That's a problem. Okay. Even worse, if the outside environment is a hydrogen environment, the boron even will escape from the surface and back to the atmosphere. In that case, we'll take out even more boron from the silicon. So the reduction of the boron concentration on the surface will become severe. Okay, become very serious problem. On the other hand, if the silicon dioxide does not like the atom, for example, phosphorus, he will try to reject the atom. So originally, the silicon dioxide layer contained some portion of the phosphorus. Because the silicon dioxide does not like phosphorus, you will cast out the phosphorus back to the silicon. So you end up, you will see the pile up of the impurity on the silicon surface. The concentration is higher on the surface. You can see the result here. Okay. That may be okay because sometimes if you have a high concentration, you just increase the current, high current rate. It won't get some defect phenomena. Might be okay. But if you have too much dopant piled up, they may cause the channel shortening. Maybe have some different problem. Okay. So that's a real situation. When you deal with the diffusion process, usually they were using oxygen and also nitrogen to carry your gas type, liquid type, or solid type material into the furnace area and for the diffusion process. Okay, so the silicon dioxide sometimes will give you some this kind of problem. Okay, so you need to remember. So the first one give you the solid type. The second one is the liquid type. So for liquid type, you need to use nitrogen gas to bring up some the liquid vapor from the solution then into the furnace. We still need to put some oxygen to oxide surface, okay, to stabilize the surface. And for the next one is gas type. So the gas type, the phosphorus or boron source will become a gas type things. So introduce 3 gas together into the furnace and a high temperature to do the diffusion process. So the diffusion process usually will take a certain time, for example, like hours, okay, to allow the dopant get into the silicon substrate, okay. So this is for diffusion process. So in addition to the diffusion process, people try to think if you want to control the dopant region more accurately and the dose more accurately, we can consider another process we call the ion implantation. Ion implantation is similar to by using the shotgun, okay, to shut the shots, get into the body, and stop at a certain kind of distance. It's very similar to shotgun, okay. So for ion implantation, it considers several important components. The first, we need to generate ions, okay. The impurity first need to become ions. When they become ions, they can be manipulated by the electric field or the magnetic fields later on. If they are neutron or they are not ion atom, they cannot be manipulated by the electric field later on. So the first one, they need to generate ions. So the gas become ions. After they become ions, the ions will go through a mass spectrometer. So by using the magnetic field to bend those ions into certain kind of angle. So in this case, we also filter out the ions that we don't want, the impurity we don't want. Because for spectrometer, different ions with different charge and different density or different weight, they will bend into different circle, will appear appear at the different tracks. After they come out, we select the ions we want, and then we accelerate the ion speed by using the accelerator. So the accelerator using electric field to speed up the speed of the ions. So the ions become shotgun, the shots in the shotgun now, shoot out from the shotgun now. So we can shoot those ions onto the final target of our wafer. Okay. And during this kind of separation, we also got some neutron. So the neutron will not be bent by our electric fields, will go directly into the collector, will be trapped and taken away. So only for those ions we want, we will bend into the substrate. And then through a scanner, because every time we got a very focused beam, okay, so the size is around like a millimeter to centimeter size. So your wafer is a 4-inch wafer, is quite large. So you need to rastering across your wafer, to scan over your wafer, to allow every region to have this kind of ions to be shoot into the design area. So it depends on the power you are using, the acceleration you are using. So the depth can be defined. So you can shoot into different depth, okay? And then they will be very concentrated at a certain kind of distance inside your surface, okay? So this is the first step. But after this step, you still cannot use these ions, okay? Because they are not taking the place of the silicon. So they don't have any function yet. So you still need to go to the second process, the annealing, the driving process, to elevate temperature, to allow the ions, the atoms, to replace the silicon, to become active. Okay? Still two steps. The first one, shoot the ions into certain distance below the surface of the silicon. The second, annealing, to activate them, to replace the silicon vacancy, and to get function. Okay? So two steps. So here we talk about the first step, the ion implantation. So different from the diffusion. Diffusion is mainly from the surface. Okay? So you always get a higher concentration on the surface, low concentration on the interior. But for ion implantation, you have the ability to adjust the depth of your shooting region. Okay. So for example, you can shoot. Look into the normal equation. Okay, too much equation will make you a little bit not that clear. So look into the figure. Okay. So for example, this is a surface of a silicon. So when you shoot the ions into the surface, you can adjust the position. We call it RP. Okay. So RP means the distance between the most concentrated region to your surface. So you can adjust the distance from a couple 100 nanometer, even deep to a couple micron. Depends on energy. If you give a lot of acceleration energy, it will go deeper. But it also depends on the atoms, the species of atoms, different atoms. So heavier atoms will stop closer to the surface, but lighter atoms will go deeper into the surface. Okay. So after you shoot all the ions into a certain stop at a certain area, they are not forming only one line. Actually, they have some kind of distribution like this. But the distribution is very, very sharp. You can see. Okay. So we usually call the first standard deviation. We call it delta RP. We call this a strago. Okay. So the total dose inside this amount, we're using a very simple equation to calculate. It's here. It's not here. On the top here. Yeah, the total dose. Yes, here. The total dose will be your center concentration NP times your strago is the first standard deviation, and then times a constant, square 2 pi. Okay. So this is the total amount of the atoms or ions you implant inside the wafer. Okay. So this is the first step. So after this step, you still need to go to the drive-in. The drive-in bring this material into the higher temperature. So the atom will start to diffuse, starting from this position to the surface and then to the deeper area as well. Both sides, go both sides. So the final profile, maybe it looks like you have a more concentration here, and the surface is a bit lower, high concentration here, and even low concentration at the interior. It's different from diffusion. Diffusion always have a high concentration on the surface. But this one, you can control the high concentration not on the surface, maybe inside some kind of depth of the material. Okay? So this is a good thing of implantation. And also the control of the dosage is more accurate than diffusion. Yeah. But there are also some downside for implantation. Implantation, because using shotgun to shot the ions into the material, actually those area for the ion passing through will cause some damage. Right? It's shotgun. Diffusion is more gentle. Yeah, you're like a thief, steal into the area. But this is using shotgun, like a robber. you get into, rush into, force into, the area. So it causes some damage. Yeah. And also for diffusion, you can put there for a very long time. You can end up get a lot of amount of ions. But for implantation, it's not easy, because you have too much concentrated ions into a small region. You will give a lot of defects in this region. Sometimes it will break the whole surface. So there's one method by using this implantation to break up a small portion of the silicon substrate. For example, 1 micron silicon substrate from the surface, separate from the surface, by using this method. Okay. So it's not easy to implant too much ions. Otherwise, you need to put the ions into different depths. You can do different depths several times. So you get more ion inside this region. But they will be very costly. Implantation is much more expensive than diffusion process. Remember that. Okay. Okay, this is roughly about the implantation. So after, so here give you two figures. The first figures give you the RP value. The RP value means the position. So the position will increase with the increase of your acceleration energy. If you have a higher acceleration energy, you got it deeper. So you can see the 0.1 micron here. Using the keV, more than 100 keV, you can have the boron into 1 micron region. It's a lighter material, a lighter atom. Compared to arsenide can go into only like a 0.2 micron in depth. Okay? So lighter material can go deeper. We're using the same energy. Okay? And also, when you increase the energy, all the atoms can go deeper. Okay? And also, the deviation for lighter material, the standard deviation is larger. Okay, so it's not that sharp. But for heavier material, heavier atom, they will stop at almost a fixed position. Okay, more concentrated position. Okay. Okay, so if you want to do the selective implantation, that means you want to only in some special area do ion implantation, but not all other area. So you can use photoresist as a mask. That's very simple. Photoresist is just spin coating. You can have the material. When you compare to silicon oxide, silicon nitride, they need to go through high temperature process. It's not that easy. Okay, so for ion implantation, using either silicon dioxide or using photoresist as a material, as a mask material, so it's much simpler. Okay. Okay, after finish the implantation, diffusion, and then we will cover something about the film deposition. For thin film deposition, we have two different ways. One is called the PVD, physical vapor deposition. The other one we call the CVD, chemical vapor deposition. For CVD, that means the whole process going through only physical process, physical way, physical mechanism, no chemical reaction. For example, we can use you can use like an evaporation method. Evaporation method, that means we heat up the material until the material beyond its melting point. Okay, then the vapor will evaporate from the surface, go into the space, then redeposit onto your surface, become thin film. So you wait a certain time, so you accumulate material become more thicker and thicker. And then you stop the evaporation process. You take out the substrate, you get a certain kind of thickness of the material you want. So that's called evaporation. So for evaporation, there are majorly two kinds of way to melt the material. The first one by using the heater, tungsten filament. Okay, so you put the material on the top of the tungsten filament. You give the current into the tungsten filament. So the tungsten will be heat up, okay, into very high temperature, depends on the material you want. So the material can be melted out. So this is called a thermal evaporation, using thermal way, okay. But this way can treat only certain kind of material like aluminum, like gold. But for some material, they have a very high melting temperature, or they have a high reactivity. With tungsten or with a substrate is not good to use. So that's why we consider the other way by using the E-beam evaporation. For E-beam evaporation, we generate electron beam using the magnetic fields to bend the beam to hit on the top of our target, the target material. So the heating of the electron beam onto the target will generate heat as well. Okay, when stop on the surface, will generate a lot of heat. So that way we can heat up many different kind of material without too much contact with the target to the container for reaction or some side effect. So by using this way, it's easier to heat up many different kind of materials, including high temperature material. Okay. So also this method can generate vapor to deposit onto your substrate. So you put your substrate on the top. So once you got the vapor from the target, the vapor will going up to stick onto your substrate on the top. Okay. So that's a usual way we do the evaporation process. And usually we put a source here using the electron beam to heat on the source, and they put our substrate wafer, for example, wafers on the top. And in order, because if you put the wafer on the top at a different position, actually you get a different deposition rate. Sometimes it's not easy to control the process. You want to, because every time when we heat up the substrate, heat up the target, you want to deposit onto as many substrates as possible, right, to reduce the cost. So that's what we need to think, how to put the wafer surrounding the source in order to allow them get a very uniform deposition on each individual substrate. So that's why when you consider a spatial we call the planetary or this kind of planetary way. The planetary way, when we consider two parameters, the one parameter is the angle phi. Okay, so when you have your wafer deviated from the center to the angle phi, you got some cosine law. The deposition rate will be reduced by the cosine law. Okay, so this is a first parameter you need to consider. The second parameter, when you put the wafer toward your source, okay, directly you consider the first phi, but also you will consider the facing. If you are not facing down, you're facing toward the center part. Okay, all the way toward the center part. You have another angle we call the theta angle, phi and theta. So this will give another cosine law. So the final deposition rate will be these two cosine law product together. Okay, so the final let's see, the final equation is not here, it's on the top. Yeah, so the final total deposition rate will be the cosine phi times cosine theta times the total material you deposit into the semi-atmosphere. Okay, semi-sphere. Okay.